What if I told you that everything you see around you, every star, every galaxy, even the space between them, was once compressed into a space smaller than a single atom? It's a staggering thought, isn't it, that the vast, seemingly infinite universe we know today began as a tiny speck of unimaginable energy, waiting to burst forth in what we now call the Big Bang. But this wasn't just an explosion of matter and light, it was the ultimate act of cosmic creativity, a moment that set the stage for everything that exists. And yet, for all we know, this is only part of the story. What came before that moment? What sparked it? And could there be other universes out there, hidden beyond the edges of our own? These aren't just questions for scientists, they're questions that touch the very essence of existence. Understanding how the universe began isn't just about unraveling the mysteries of the cosmos. It's about exploring who we are and where we fit into this grand tapestry. In this video, we'll take you on a journey through the most fascinating theories about the birth of the universe. From the explosive beginnings of the Big Bang to the mind-bending possibilities of multiverses, we'll dive into the ideas that challenge our understanding of reality itself. So, if you've ever looked up at the night sky and wondered how it all began, you're in the right place. Let's embark on this cosmic adventure together. Imagine, for a moment, standing at the edge of an infinite void, a place where time, space, and matter don't yet exist. Suddenly, in an unimaginable flash, everything begins. This is the Big Bang, the cosmic event that marks the birth of our universe. It's not just an explosion in the traditional sense, but the very moment when existence itself burst into being. From this single, incomprehensible instant, the universe began to expand, evolve, and take the shape we see today, a vast, intricate tapestry of galaxies, stars, and planets. The story of this groundbreaking idea starts not in the stars, but here on Earth with two brilliant minds. In the early 20th century, a Belgian priest and physicist named Georges Lemaitre proposed a radical idea that the universe had a beginning. He called it the primeval atom, a single point of infinite density from which everything originated. Around the same time, astronomer Edwin Hubble made a staggering discovery. By observing distant galaxies, he noticed that they were moving away from us, and the farther away they were, the faster they seemed to be receding. This observation became known as Hubble's law, and it provided the first tangible evidence that the universe was expanding. Together, these discoveries laid the foundation for what we now call the Big Bang theory. But how do we know this theory holds water? One of the most compelling pieces of evidence comes from something we can't even see with the naked eye: the cosmic microwave background radiation. Think of it as the afterglow of the Big Bang, a faint whisper of energy left over from that initial burst. It's like finding the warmth of a campfire long after the flames have died down. This radiation, discovered accidentally in the 1960s, is everywhere in the universe, and it matches perfectly with what scientists predicted the Big Bang would leave behind. To help visualize the universe's expansion, picture a balloon with dots drawn all over its surface. As you inflate the balloon, the dots move farther apart, just like galaxies in our expanding universe. It's not that the galaxies themselves are moving through space, it's that space itself is stretching, carrying them along with it. This simple analogy helps us grasp a concept that's otherwise almost impossible to wrap our minds around. The Big Bang theory isn't just a scientific idea, it's the cornerstone of modern cosmology. It provides a framework for understanding how the universe began, how it evolved, and even how it might end. It's the starting point for exploring some of the most profound questions we can ask. Where did we come from? What is the universe made of? And what does the future hold? As we dive deeper into the mysteries of the cosmos, the Big Bang remains our guiding light, illuminating the path forward. In the moments following the Big Bang, the universe experienced something extraordinary, a growth spurt so rapid it defies imagination. This brief but transformative phase is known as cosmic inflation. Picture this: the universe, still in its infancy, expanded faster than the speed of light, stretching from the size of a single atom to something astronomically larger in a fraction of a second. It's like taking a tiny, microscopic speck and suddenly ballooning it into something the size of a galaxy. But how did this idea come about? Enter Alan Guth, a physicist whose groundbreaking work in the 1980s proposed inflation as a solution to some of the universe's most puzzling mysteries. One of those mysteries is the horizon problem. Why does the universe look so uniform? If you look in opposite directions in the night sky, the temperature and structure of the cosmos appear remarkably similar, even though there hasn't been enough time since the Big Bang for these regions to exchange information. Inflation explains this by suggesting that the entire observable universe was once a tiny, interconnected region that expanded so quickly it preserved its uniformity. Then there's the flatness problem. The universe appears incredibly flat on large scales, like a perfectly balanced sheet of paper. Inflation smoothed out any initial curvature, stretching space-time until it became nearly flat. To make this easier to grasp, think of inflation like a loaf of bread rising in the oven. Before baking, the dough is small and dense, but as it heats up, it expands rapidly. Tiny seeds or grains in the dough representing quantum fluctuations get stretched out too, becoming the foundation for the bread's texture. In the same way, quantum fluctuations during inflation were magnified, creating the seeds for the large-scale structure of the universe. These tiny ripples eventually grew into the galaxies, stars, and cosmic web we see today. But here's the kicker: while inflation answers many questions, it also raises new ones. What caused this sudden, explosive expansion? What mechanism set it into motion? These are the mysteries that keep physicists awake at night, searching for clues in the faint echoes of the early universe. And as we'll see next, those echoes might hold the key to understanding what came before inflation, and perhaps even what lies beyond our current understanding of the cosmos. Picture the universe in its earliest moments, a vast, seething ocean of energy, where even the tiniest ripples held the potential to shape everything we see today. These ripples, known as quantum fluctuations, were born in the quantum realm, where particles and energy flicker in and out of existence in an almost ghostly dance. During the rapid expansion of inflation, these microscopic fluctuations were stretched across unimaginable distances, becoming the seeds of cosmic structure. Like ripples spreading across a pond, these tiny variations in energy density began to grow, setting the stage for the galaxies, stars, and planets that would one day fill the universe. But how did these faint ripples become the colossal structures we observe today? Enter dark matter, the invisible scaffolding of the cosmos. While ordinary matter interacts with light and forms the stars and galaxies we can see, dark matter's gravitational pull played a crucial role in amplifying those early fluctuations. Think of it like this: if quantum fluctuations were the faint whispers of the universe's infancy, dark matter was the megaphone that turned them into a cosmic roar. Over billions of years, these amplified fluctuations coalesced into the vast web of galaxies and clusters that define the universe's large-scale structure. Recent discoveries have given us an extraordinary glimpse into these ancient ripples. The Planck satellite, for instance, mapped the cosmic microwave background, an afterglow of the Big Bang, with unprecedented precision. This faint radiation carries imprints of those early quantum fluctuations, like a cosmic fingerprint preserved in the fabric of space-time. These measurements have not only confirmed the predictions of inflation, but also deepened our understanding of how the universe evolved from a chaotic, jumbled state into the ordered cosmos we inhabit today. Yet, as we marvel at the intricate tapestry of the observable universe, a tantalizing question lingers: what lies beyond the cosmic horizon? The light from these distant regions hasn't had time to reach us, leaving vast swaths of the universe shrouded in mystery. Could there be other structures, other galaxies, or even other universes forever hidden from our view? The story of quantum fluctuations is just the beginning, a prologue to a cosmic narrative that stretches far beyond what we can currently see. What if our universe is just one tiny bubble floating in an endless cosmic sea of possibilities? This is the heart of the Multiverse Hypothesis, a mind-bending idea that suggests our universe might not be alone. Imagine an infinite expanse where countless other universes exist, each with its own unique set of physical laws. Some might have stronger gravity, making stars burn brighter and faster, while others might have weaker gravity where planets drift lazily through space. These bubble universes could be as varied as grains of sand on a beach, each one a self-contained reality with its own rules. But how does this idea even emerge from science? It all ties back to inflation theory, the idea that our universe expanded exponentially in the first moments after the Big Bang. Inflation doesn't just stop in one place, it's eternal, creating pocket after pocket of space-time, each one a new universe. Think of it like a pot of boiling water. Bubbles form, expand, and detach from one another, floating off into the void. In this cosmic soup, our universe is just one bubble among trillions. Now, here's where it gets really fascinating. If other universes exist, they might not play by the same rules as ours. Imagine a universe where the speed of light is slower or where time flows backward. Or consider a world where the fundamental constants like the charge of an electron or the strength of nuclear forces are just slightly different. In some of these universes, life as we know it might be impossible, while in others, it could thrive under entirely alien conditions. This brings us to the Anthropic principle, a thought-provoking idea that suggests our universe seems fine-tuned for life because, well, we're here to observe it. If there are countless universes out there, each with different laws, it's no surprise that at least one of them would be just right for life to emerge. But does this mean the multiverse is a scientific fact? Not quite. While the idea is compelling, it's still largely in the realm of speculation. Scientists are working on ways to test the multiverse hypothesis, but for now, it remains one of the most tantalizing and controversial ideas in cosmology. So, could we ever prove the existence of other universes? Or is the multiverse destined to stay in the realm of imagination? To explore that question, we need to look at the cutting-edge tools and theories that might one day bring this cosmic mystery into focus. One of the most ambitious ideas in modern physics is string theory, a framework that seeks to unify all the fundamental forces of nature under one elegant umbrella. Picture this: instead of particles being tiny dots, they're actually incredibly small, vibrating strings. The way these strings vibrate determines the properties of everything in the universe, like a cosmic orchestra where each note corresponds to a different particle or force. But here's where it gets even more fascinating. String theory suggests that our universe might not be alone. In fact, it proposes a vast landscape of possible universes, each with its own unique set of rules and properties. Think of it like a cosmic jukebox. Every time you press play, you get a different tune, a different universe. The shape and size of the extra dimensions in string theory, which are curled up so small we can't detect them, determine the song each universe plays. Some universes might have stronger gravity, others might allow for different types of matter, and some might not even support life as we know it. It's a wild idea, but one that could explain why our universe seems so finely tuned for life. Maybe we're just one of countless possibilities, but as captivating as string theory is, it comes with its own set of challenges. For one, testing it is no easy feat. The energies required to probe the tiniest scales where these strings exist are far beyond anything we can currently achieve. It's like trying to hear a whisper in a hurricane. Our tools just aren't sensitive enough yet. And while the math behind string theory is beautiful, it's also incredibly complex, leaving some scientists to wonder if it's the final answer or just a stepping stone to something even deeper. This brings us to a profound question. Did the universe truly have a beginning, or has it always existed in some form? string theory hints at the possibility of a multiverse, where universes are born, collide, and even dissolve into one another. Could our universe be just one chapter in an infinite cosmic story? As we explore these ideas, we're reminded that the search for answers is as much about the journey as it is about the destination. And the universe, it seems, is full of surprises waiting to be uncovered. What if the universe isn't a one-time event but an endless dance of creation and renewal? This is the core idea behind the cyclic model, a fascinating theory that suggests our universe has no true beginning or end. Instead, it undergoes an infinite series of expansions and contractions, like a cosmic accordion breathing in and out across eternity. Unlike the Big Bang, which starts with a single explosive moment, the cyclic model avoids the problem of a singularity, a point of infinite density, by proposing that the universe bounces from one cycle to the next. Each contraction leads not to destruction but to rebirth, as the universe collapses and then springs back into a new phase of expansion. Central to this model is dark energy, the mysterious force that accelerates the universe's expansion. In this theory, dark energy doesn't just push the universe apart, it also plays a key role in triggering the next contraction. Picture it as the engine of this cosmic rhythm, driving the cycles forward. But here's the challenge. If the universe has gone through countless cycles before, where's the evidence? The problem is that each cycle might completely erase traces of the one before it, leaving us with no way to peer into the past. It's like trying to read a book where every new chapter wipes the previous one clean. This raises intriguing questions about time itself. If the universe cycles endlessly, does time have a beginning, or is it also caught in this eternal loop? Some theories suggest that time might reset with each cycle, while others propose that it flows continuously, connecting the cycles in a vast, unbroken timeline. Either way, the cyclic model forces us to rethink not just how the universe began, but also how we understand time and existence on the grandest scale. As we explore these ideas, it's worth considering how they challenge our everyday perception of beginnings and endings. Could the universe really be an endless loop with no true start or finish? And if so, what does that mean for our place within it? These questions take us deeper into the fabric of reality, where the origins of the universe might not be a single moment but a never-ending story. But what about time itself? Did it begin with the Big Bang, or is it something that has always existed? This is one of the most mind-bending questions in cosmology. If the Big Bang marked the beginning of everything space, matter, energy, then did time also start ticking at that very moment? Or was there something before it, a state where time didn't even exist? Picture this, a clock ticking backward, counting down to zero. What happens when it reaches that point? Does time simply stop, or does it cease to have any meaning at all? Some theorists suggest that before the Big Bang, the universe existed in a kind of timeless quantum state. In this state, the usual rules of cause and effect break down. There's no before or after, no sequence of events, just a strange, fluctuating realm where traditional ideas of time don't apply. This brings us to loop quantum gravity, a theory that tries to describe the universe's birth without invoking a singularity, a point of infinite density. Instead, it proposes that the universe emerged from a quantum foam, a chaotic yet structured state where time as we know it didn't exist. In this framework, the Big Bang wasn't the beginning of time, but rather a transition from one state to another. To grasp this, think of time not as a straight line, but as a web of possibilities where past, present, and future are all interconnected. Quantum mechanics plays a crucial role here, as it allows for these strange, counterintuitive ideas to take shape. The early universe, governed by quantum laws, was a place where particles could pop in and out of existence, and time itself could behave in ways that defy our everyday experience. As we explore these ideas, it's clear that the nature of time is far more complex than we often assume. It's not just a backdrop to the universe, but something deeply intertwined with its very fabric. And this leads us to the next big question. How did quantum mechanics shape the early moments of the cosmos? What role did these tiny, unpredictable particles play in the birth of everything we see today? Now let's zoom in on one of the most profound puzzles in modern physics, quantum gravity. Imagine trying to describe the universe in its very first moments, when it was smaller than an atom and hotter than a star. At that scale, the rules we know break down. Einstein's theory of general relativity, which beautifully explains the dance of planets and galaxies, clashes with quantum mechanics, the science of the tiny, unpredictable world of particles. To truly understand the birth of the universe, we need a theory that can bridge this gap, a theory of quantum gravity. Two leading candidates have emerged in this quest: loop quantum gravity and string theory. Loop quantum gravity visualizes spacetime as a network of tiny, woven loops, a cosmic tapestry where every thread represents a quantum of space. Instead of a smooth, continuous fabric, spacetime becomes a patchwork of discrete, interconnected pieces. It's like zooming in on a woven blanket and discovering that what looked smooth from afar is actually made of countless tiny knots and links. This theory suggests that spacetime itself has a structure, a granularity at the smallest scales. On the other hand, string theory takes a different approach. It proposes that the fundamental building blocks of the universe aren't point-like particles, but tiny, vibrating strings. These strings can twist and vibrate in different ways, giving rise to all the particles and forces we observe. Think of it like a cosmic symphony, where every note played by these strings creates a different aspect of reality. String theory also suggests that spacetime might have extra dimensions, hidden layers curled up so tightly that we can't perceive them. But here's the catch: testing these theories is incredibly difficult. The scales at which quantum gravity operates are unimaginably small, down to the Planck scale, where distances are a billionth of a billionth of a billionth of a meter. Our current technology is light years away from probing such extremes. It's like trying to study the details of a snowflake from miles away with a telescope. Without direct experiments, physicists rely on mathematical elegance and consistency to guide them. Despite these challenges, the search for quantum gravity is more than just an intellectual exercise. It's a journey to uncover the very fabric of reality, to understand how the universe stitches itself together at the deepest level. And as we explore these theories, we begin to see hints of a deeper truth. That symmetry, a kind of cosmic balance, might have played a crucial role in shaping the universe from its very first moments. Imagine a pencil perfectly balanced on its tip, a fleeting moment of equilibrium where every direction looks the same. But then, inevitably, it tips over, breaking that perfect symmetry. Now, think of the early universe. In its first moments, it was a place of incredible symmetry, where all the fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces were unified into a single, all-encompassing force. But just like that pencil, the universe couldn't stay perfectly balanced forever. This is where the concept of symmetry breaking comes into play, a process that transformed the cosmos and gave rise to the forces and particles we know today. Symmetry breaking is the idea that as the universe cooled and expanded, it underwent dramatic changes, shattering its initial uniformity. Think of it like water freezing into ice. In its liquid form, water looks the same in every direction, but as it freezes, it forms a crystalline structure, breaking that symmetry. Similarly, the early universe transitioned through phases where its symmetries were broken, leading to the emergence of distinct forces and particles. One of the most famous examples of this is the Higgs field, an invisible energy field that permeates the entire universe. When particles interact with this field, they gain mass, a process that's essential for the existence of atoms, stars, and ultimately us. Without symmetry breaking, the universe would have remained a featureless soup of energy, incapable of forming the complex structures we see today. But why does this matter? Symmetry breaking isn't just a cosmic quirk, it's the key to understanding how the universe works. It explains why particles like electrons and quarks have mass, why the forces of nature behave the way they do, and why the universe isn't just a chaotic jumble of energy. It's also deeply tied to the idea of unification, the dream of physicists to describe all the fundamental forces with a single, elegant theory. Symmetry breaking is the bridge between that unified early universe and the diverse, dynamic cosmos we inhabit today. As we look deeper into this process, we begin to see how it connects to even bigger mysteries like dark matter and dark energy. These enigmatic components of the universe might also be rooted in the hidden symmetries of the cosmos waiting to be uncovered. But that's a story for another moment. For now, let's marvel at the elegance of symmetry breaking, a process that began with a perfectly balanced universe and ended with the rich, complex tapestry of existence we call home. Picture this: everything we see around us, the stars, galaxies, and even the vast emptiness of space, makes up less than 5% of the universe. The rest, it's hidden in plain sight, composed of two mysterious forces, dark matter and dark energy. These invisible architects hold the keys to understanding the universe's structure and its ultimate fate. Dark matter is the unseen glue that binds galaxies together. Though it doesn't emit light or interact with ordinary matter in ways we can easily detect, its presence is undeniable through its gravitational effects. Imagine an invisible hand guiding the motion of stars within galaxies, or clusters of galaxies moving in ways that defy ordinary physics. Without dark matter, galaxies would fly apart, unable to hold their shape against the forces of gravity and motion. It's like trying to build a sandcastle without any sand. Dark matter is the essential ingredient that keeps the cosmic structure intact. But dark matter is only half the story. Enter dark energy, an even more elusive force that's pushing the universe apart at an ever-accelerating rate. Think of it as an invisible wind, gently but relentlessly expanding the fabric of space itself. Over billions of years, this force has shaped the universe on the largest scales, stretching it into the vast, interconnected web of galaxies we observe today. While dark matter holds things together, dark energy is the cosmic force driving them apart, creating a delicate balance that defines our universe's evolution. Scientists have been working tirelessly to unravel these mysteries, from deep underground detectors searching for dark matter particles to telescopes mapping the universe's expansion to understand dark energy. The quest to uncover their secrets is one of the most exciting frontiers in modern science. Yet, despite decades of research, dark matter and dark energy remain elusive, reminding us just how much we still have to learn about the cosmos. As we peel back the layers of these invisible forces, another cosmic enigma emerges: black holes. These mysterious objects, born from the collapse of massive stars, play a crucial role in shaping galaxies and influencing the universe's evolution. But how do they fit into the grand story of how the universe began? That's where our journey takes us next. Black holes are often thought of as cosmic vacuum cleaners, devouring everything in their path. But what if they're more than just destructive forces? What if they're windows into the very birth of the universe itself? At the heart of every black hole lies a singularity, a point where gravity becomes infinitely strong, and the laws of physics as we know them simply stop working. It's a place where time and space warp beyond recognition, creating conditions so extreme that they might just mirror the universe's earliest moments. Picture this: as you approach a black hole's event horizon, the boundary beyond which nothing can escape, you're greeted by a swirling vortex of energy and light. It's like standing at the edge of a cosmic whirlpool, where the rules of reality are rewritten with every passing second. Some scientists believe that this chaotic environment could resemble the conditions present during the Big Bang, a moment when all matter, energy, and space were compressed into an infinitely dense point. Could black holes, then, be tiny echoes of that primordial explosion? One of the most fascinating theories tied to black holes is the holographic principle. This idea proposes that all the information about the universe, everything that ever was or will be, could be encoded on a black hole's surface. Think of it like a cosmic hard drive where the three-dimensional universe is projected from a two-dimensional boundary. If true, this would mean that black holes aren't just gravitational monsters, they are also repositories of the universe's deepest secrets. But here's the real question. If black holes can mimic the conditions of the Big Bang, what does that tell us about the nature of the universe itself? Is the cosmos finite, with edges and boundaries we've yet to discover, or is it infinite, stretching endlessly in all directions? As we peer into the abyss of a black hole, we're not just exploring the limits of space and time, we're also searching for answers to the mysteries that define our very existence. So, what does the universe look like? Is it a vast, endless expanse, or does it have a shape, a boundary, a limit? This question has fascinated scientists and philosophers for centuries, and today we're closer than ever to understanding the geometry of the cosmos. The shape of the universe isn't just a matter of curiosity, it's a fundamental piece of the puzzle that tells us how the universe behaves, how it began, and what its ultimate fate might be. When we talk about the shape of the universe, we're really talking about its geometry. Is it flat, like an infinitely large sheet of paper? Is it open, curving outward like a saddle? Or is it closed, bending back on itself like the surface of a sphere? These are the three main possibilities, and each one carries profound implications for the nature of reality. To figure this out, scientists turn to one of the most important tools in cosmology, the cosmic microwave background, or CMB. This faint glow of radiation left over from the Big Bang is like a snapshot of the universe when it was just a few 100,000 years old. By studying tiny fluctuations in the CMB, researchers can map the geometry of the universe on the largest scales. Imagine the universe as the surface of a balloon. If the balloon is perfectly inflated, its surface is flat, and two parallel lines drawn on it will never meet. This is what a flat universe would look like, a geometry where the rules of Euclidean space apply, and the universe extends infinitely in all directions. But if the balloon isn't fully inflated, its surface curves. In a closed universe like a sphere, those parallel lines would eventually cross, and if you traveled far enough in a straight line, you'd end up back where you started. On the other hand, an open universe would curve outward like a saddle, and those lines would diverge indefinitely. So, what do the measurements tell us? Surprisingly, the data from the CMB strongly suggests that the universe is flat, or at least extremely close to it. This means that, on the largest scales, the universe doesn't curve back on itself or bend outward. It just keeps going, stretching out into infinity. But here's where things get even more intriguing. A flat universe could still be finite, like a video game world that loops back on itself when you reach the edge. This would mean that, theoretically, if you traveled far enough in one direction, you might eventually return to your starting point. But if the universe is both flat and infinite, the possibilities are truly mind-boggling. The shape of the universe isn't just a matter of geometry, it also has profound implications for the future. If the universe is closed, it might eventually collapse back in on itself in a big crunch. If it's open, it could continue expanding forever, growing colder and darker as stars burn out and galaxies drift apart. And if it's flat, as the evidence suggests, the expansion could slow down but never stop, leading to a universe that grows increasingly vast and empty over time. But how does this all connect to the broader story of the universe's evolution? To answer that, we need to look at another key player in the cosmic drama, entropy. Entropy is the measure of disorder in a system, and it plays a crucial role in shaping the universe's destiny. As the universe expands, entropy increases, driving the cosmos toward a state of maximum disorder. This process, known as the heat death of the universe, is one of the most fascinating and chilling ideas in cosmology, and it's where our journey takes us next. Let's take a moment to think about time not as a clock ticking away, but as something far more profound. Time, as we experience it, always moves forward, never backward. But why is that? What makes time a one-way street? The answer lies in a fascinating concept called entropy. Entropy is essentially a measure of disorder or randomness in a system, and it's the reason why certain processes in the universe seem irreversible. Picture this: you drop a glass and it shatters into pieces. You'd never expect the shards to suddenly leap back together into a perfect glass. That's entropy at work, a natural tendency toward increasing disorder. Now, let's make this idea a bit more tangible. Imagine an ice cube sitting on your kitchen counter. As it melts, it transitions from a solid, orderly structure into a puddle of water, a state with far more disorder. That puddle won't spontaneously refreeze into a perfect cube unless you intervene. This simple example illustrates how entropy increases over time, driving the arrow of time forward. But here's where it gets even more intriguing. Scientists believe the early universe started in an incredibly low entropy state, a state of extreme order. Think of it as the ultimate pristine ice cube, perfectly formed and untouched. Over billions of years, that order has been unraveling, giving rise to the complexity we see today: galaxies, stars, planets, and even life itself. It's almost poetic. The universe's increasing entropy is what allowed it to evolve into such a rich and dynamic place. Yet, this same force that drives complexity might also hold the key to the universe's ultimate fate. If entropy continues to rise unchecked, the universe could eventually reach a state of maximum disorder, a scenario known as the heat death of the universe. This isn't a dramatic explosion or collapse, but rather a slow, quiet fading into uniformity, where energy is spread so thinly that nothing new can happen. It's a chilling thought, but one that underscores the profound role entropy plays in shaping not just the universe's past and present, but its future as well. So, as we marvel at the intricate dance of order and disorder, we're reminded that the arrow of time isn't just a feature of our everyday lives, it's a fundamental property of the cosmos itself. And as we look ahead, we'll explore how this relentless march of entropy might lead us to the universe's final chapter. Picture a universe that has stretched itself thin, its once vibrant energy now spread so evenly that nothing stirs. No stars burn, no planets orbit, and no life exists. This is the heat death of the universe, a chilling prediction of how our cosmos might meet its end. In this scenario, the universe reaches a state of maximum entropy, where all energy is evenly distributed, and no usable energy remains. It's like a campfire that's burned down to ash. Every ember has cooled, every flicker of heat has dissipated, leaving only a cold, dark stillness. But why does this happen? It all comes down to the relentless march of entropy, the natural tendency of systems to move toward disorder. Over trillions upon trillions of years, galaxies will exhaust their fuel, stars will burn out, and black holes will evaporate. Eventually, the universe becomes a vast, featureless expanse where even the slightest temperature differences vanish. No work can be done, no motion occurs, and time itself becomes meaningless. It's a cosmic finale that feels eerily silent and eternal. Yet, the heat death isn't the only possible ending. Some theories suggest a big crunch, where the universe stops expanding and collapses back in on itself in a fiery reverse of the Big Bang. Others propose a big rip, where the universe's expansion accelerates so violently that even atoms are torn apart. Each of these scenarios paints a dramatically different picture of the cosmos's fate. The Big Crunch offers a cyclical rebirth, while the Big Rip is a catastrophic, explosive end. But compared to the heat death, these alternatives feel almost merciful, a quick, dramatic collapse versus an endless, cold slumber. This leads us to an intriguing question. Could the universe be cyclic? could it expand, collapse, and expand again in an infinite loop? Some scientists speculate that this might be possible, offering a glimmer of hope against the bleakness of heat death. If the universe is cyclic, then perhaps every ending is just the beginning of something new. But for now, these ideas remain tantalizing possibilities, waiting for future discoveries to shed more light. As we ponder these cosmic destinies, one thing becomes clear: the fate of the universe is as mysterious as its origins. Whether it ends in heat death, a big crunch, or a big rip, the story of the universe is far from over, and its final chapter is still being written. Imagine the universe as a cosmic rubber band, stretching out further and further over billions of years. But what if, instead of stretching forever, that rubber band suddenly snapped back? This is the essence of the Big Crunch, a dramatic scenario where the universe stops expanding and begins to collapse in on itself. It's like hitting rewind on the Big Bang, with everything that once spread out hurtling back toward a single, infinitely dense point, a singularity. This idea hinges on gravity, the force that pulls objects together, eventually overpowering the mysterious dark energy that's currently driving the universe's expansion. If gravity wins this cosmic tug of war, galaxies, stars, and even the fabric of space itself would begin to contract. Over time, the universe would grow hotter and denser as it shrinks, culminating in a fiery, chaotic end where all matter and energy are crushed into an unimaginably small point. To visualize this, think of a star collapsing into a black hole, but on a universal scale. Instead of just one star, it's every star, every planet, every atom in existence. The Big Crunch isn't just an ending, it's also a beginning. Some theories suggest that this singularity could trigger another Big Bang, creating a new universe in an endless cycle of expansion and collapse. But for the Big Crunch to happen, certain conditions must be met. The universe's expansion would need to slow down significantly, and gravity would have to become the dominant force. So far, observations suggest that dark energy is still in the driver's seat, pushing galaxies apart faster and faster. But the Big Crunch remains a fascinating possibility, a reminder that the universe's fate is far from settled. And speaking of cosmic endings, there's another dramatic possibility on the horizon. One where the universe doesn't collapse but instead tears itself apart. This brings us to the Big Rip, a scenario where dark energy grows so powerful that it overwhelms even the forces holding atoms together. But that's a story for the next chapter in our exploration of the universe's ultimate destiny. Picture a universe where the very fabric of existence is ripped apart, not by a cataclysmic explosion, but by an invisible force growing stronger with time. This is the Big Rip, a haunting scenario where dark energy, the mysterious force driving the universe's accelerated expansion, doesn't just push galaxies apart, it tears them to pieces. Over billions of years, the repulsive force of dark energy would intensify, overpowering gravity, the glue that holds everything together. Galaxies would be ripped from one another, stars torn from their orbits, and even planets and atoms shredded into their most basic components. In the end, the universe would become a desolate expanse of isolated particles, a cosmic wasteland where no structure, no light, and no life could survive. To visualize this, think of the universe as a vast cosmic tapestry. Right now, it's stretched and expanding, but in the Big Rip scenario, the stretching becomes violent and unrelenting. The threads of the tapestry, galaxies, stars, and even the bonds between atoms are pulled apart until nothing remains but loose, disconnected threads. It's a dramatic and unsettling end, one that raises profound questions about the nature of dark energy and the ultimate fate of everything we know. But is this scenario more than just a theoretical possibility? Scientists have been studying the behavior of dark energy to determine whether the Big Rip is a plausible outcome. Some observations suggest that dark energy's strength remains constant over time, which would make the Big Rip less likely. However, other models propose that dark energy could grow stronger, potentially leading to this catastrophic end. The truth is, we don't yet have enough data to say for certain. What we do know is that the Big Rip serves as a stark reminder of how much we still have to learn about the forces shaping our universe. This brings us to the next piece of the puzzle, the role of quantum mechanics in the universe's fate. If the Big Rip represents one extreme where dark energy dominates and destroys, quantum mechanics offers a completely different perspective, one that might just hold the key to understanding the universe's ultimate destiny. When we think about the universe's ultimate fate, it's easy to picture grand, sweeping forces like gravity or dark energy shaping its destiny. But what if the tiniest particles, the ones governed by the strange rules of quantum mechanics, hold the key to the cosmos's long-term evolution? This is where things get truly mind-bending. Quantum mechanics, the science of the microscopic, doesn't just affect atoms and particles. It could have cosmic consequences that ripple across the vast expanse of space and time. One of the most fascinating ideas is quantum tunneling. Imagine a particle trapped behind an energy barrier, like a ball resting in a valley. In the classical world, that ball would need a lot of energy to climb out. But in the quantum realm, particles can sometimes tunnel through barriers without any extra energy at all. It's as if the ball suddenly appears on the other side of the hill without ever climbing over it. Now, scale this up to the universe. Could quantum tunneling trigger events that rewrite the very fabric of reality? It's not just science fiction. Scientists have theorized that quantum effects could lead to sudden, unexpected changes in the cosmos, like the decay of a vacuum state, which we'll get to in a moment. Then there's vacuum decay. Picture the universe as a vast, stable field like a calm lake. But beneath that surface, there's a deeper, more stable state waiting to be discovered. If a tiny region of space were to transition to this lower energy state, it could create a bubble that expands at the speed of light, rewriting the laws of physics as it grows. This isn't just a hypothetical, it's a real possibility rooted in quantum field theory. And the kicker, it could happen at any moment without warning. It's like a cosmic dice roll with the fate of the universe hanging in the balance. But quantum mechanics doesn't just threaten to unravel the universe, it could also create new ones. Imagine a random quantum fluctuation, a tiny blip in the fabric of space-time. Under the right conditions, this blip could grow into an entirely new universe, complete with its own laws of physics. It's a concept that feels more at home in a sci-fi novel than in a physics textbook, yet it's a serious topic of discussion among cosmologists. This idea of a baby universe branching off from our own opens up a whole new realm of possibilities, one where our universe might just be one of countless others in a vast, ever-expanding multiverse. So as we peer into the quantum realm, we're left with a profound realization. The universe's fate might not be written in stone. Instead, it could be shaped by the unpredictable, probabilistic nature of quantum events. And if that's the case, then the cosmos is far more dynamic and far stranger than we ever imagined. Imagine if our universe could give birth not to planets or stars, but to entirely new universes. It might sound like science fiction, but some of the most fascinating theories in cosmology suggest that this could be possible. Picture a cosmic family tree where our universe is just one branch and countless others sprout from it like new growth. This is the intriguing idea of baby universes, also known as daughter universes. These cosmic offspring could emerge through processes like black hole formation or quantum fluctuations, tiny ripples in the fabric of space-time that might trigger the birth of an entirely new cosmos. But here's where it gets even more mind-bending. These baby universes might not follow the same rules as ours. They could have entirely different physical laws. Gravity might behave differently, the speed of light could vary, or even the fundamental particles we know might not exist. This means that if such universes exist, they could be wildly diverse, creating a multiverse that's almost impossible to fully comprehend. Think of it like a tree branching out in every direction, with each branch representing a universe with its own unique set of rules. Now you might wonder, how could we ever detect or interact with these baby universes? The truth is, it's incredibly difficult. If they exist, they're likely completely separate from our own universe, isolated by the very fabric of space and time. It's like trying to peer into a parallel world that's sealed off from ours by an invisible barrier. Even with the most advanced technology, we're limited by the laws of our own universe, which might prevent us from ever reaching or observing these cosmic siblings. But that hasn't stopped scientists from theorizing and exploring the possibilities. This idea of baby universes not only challenges our understanding of existence, but also opens the door to even bigger questions. If our universe is just one of many, what does that mean for the role of consciousness in shaping reality? Could consciousness itself play a part in how these universes form or evolve? As we dive deeper into these mysteries, the line between science and philosophy begins to blur, inviting us to rethink what we know about the cosmos and our place within it. What if consciousness isn't just a byproduct of the universe, but something far more fundamental, something that might even shape reality itself? This idea, as wild as it sounds, isn't just science fiction. In fact, some of the most intriguing theories in physics and philosophy suggest that consciousness could be deeply intertwined with the fabric of the cosmos. One such theory is panpsychism, the idea that consciousness is a basic property of the universe, like mass or charge. In this view, even the smallest particles might have some form of awareness. It's not that electrons are thinking or feeling in the way we do, but rather that consciousness could exist on a spectrum, from the simplest forms to the complex self-awareness we experience as humans. Think of it like this: if the universe is a symphony, consciousness might be the underlying melody, present in every note from the tiniest vibration to the grandest crescendo. To challenge our understanding of reality, we can turn to thought experiments like Schrödinger's cat. You've probably heard of this famous paradox: a cat in a box is both alive and dead until someone observes it. While this experiment was originally designed to highlight the strange nature of quantum mechanics, it also raises profound questions about the role of the observer. Does consciousness, our act of observing, somehow influence the outcome? Could it be that reality only solidifies when a conscious mind interacts with it? These questions push us to rethink not just how the universe works, but our place within it. If consciousness truly is a fundamental aspect of the universe, the implications are staggering. It could mean that the cosmos isn't just a cold, indifferent expanse of matter and energy, but something more alive, more interconnected than we've ever imagined. Some scientists and philosophers even speculate that the universe might be fine-tuned for consciousness, as if it were designed to give rise to beings capable of observing and reflecting on its existence. This brings us to the anthropic principle, the idea that the universe's laws and constants appear perfectly calibrated to allow for life and consciousness. But is this just a cosmic coincidence, or is there something deeper at play? Could consciousness itself be a driving force in the universe's evolution? As we explore these questions, we're not just unraveling the mysteries of the cosmos, we're also uncovering new ways to understand ourselves and our place in the grand tapestry of existence. Have you ever stopped to think about how perfectly calibrated the universe seems to be for life as we know it? It's not just luck, it's something far more intriguing. This is where the anthropic principle comes into play. At its core, the anthropic principle suggests that the universe's physical constants, things like the strength of gravity, the mass of an electron, or the speed of light, are not arbitrary. Instead, they appear to be precisely fine-tuned to create the conditions necessary for life to emerge. If any of these constants were even slightly different, life as we know it might never have existed. Take gravity, for example. If it were just a tiny bit stronger, stars would burn through their fuel too quickly, collapsing into black holes before planets could form. On the other hand, if gravity were weaker, stars might never ignite at all, or consider the mass of an electron. If it were even slightly heavier or lighter, atoms wouldn't bond together properly, making complex molecules and life itself impossible. These aren't just minor details, they're fundamental building blocks of reality, and their precise values seem almost too perfect to be accidental. But what does this fine-tuning mean? Some scientists and philosophers argue that it points to the existence of a multiverse, a vast collection of universes, each with its own set of physical constants. In this view, we just happen to live in the one universe where the numbers lined up perfectly for life. Others suggest a more controversial idea, that this fine-tuning implies the presence of a designer, a force or intelligence that set the parameters of the universe with intention. Both ideas are deeply thought-provoking, and while they're not mutually exclusive, they challenge us to rethink our understanding of existence itself. The Anthropic principle doesn't just stop at physics, it opens the door to profound philosophical questions. Are we here by chance, or is there something deeper at work? And if the universe is fine-tuned for life, what does that say about our place in it? These questions might not have easy answers, but they remind us of the extraordinary nature of the cosmos we inhabit. As we ponder these ideas, it's worth considering how mathematics, the language of the universe, helps us make sense of it all. From the precise equations that describe the behavior of particles to the elegant formulas that map the expansion of space, math gives us a framework to understand the fine-tuned nature of reality. And that's where we'll turn next, to the role of mathematics in unraveling the mysteries of the universe. Have you ever wondered how the universe seems to follow a set of invisible rules, almost as if it's playing by a hidden script? That script, it turns out, is written in the language of mathematics. From the spiraling arms of galaxies to the quantum dance of particles, everything around us can be described and predicted using mathematical equations. It's as if the universe is whispering its secrets to us through numbers, shapes, and patterns. Take symmetry groups, for example. These are mathematical tools that help us understand how objects can look identical after being rotated, flipped, or shifted. Think of a snowflake. No matter how you turn it, its intricate design remains the same. This same principle applies to fundamental forces like electromagnetism and the behavior of particles at the smallest scales. Symmetry isn't just a pretty feature, it's a cornerstone of how the universe operates. Then there are differential equations, which might sound intimidating, but they're essentially the universe's way of explaining change. Whether it's the motion of planets orbiting a star or the way heat spreads through a room, differential equations let us map out how things evolve over time. They're like the cosmic choreographers, dictating the steps of everything from the smallest atoms to the largest galaxies. But here's the real mystery. Why does mathematics work so well? Why does this abstract system created by human minds align so perfectly with the behavior of the natural world? Some scientists and philosophers argue that mathematics isn't just a tool we invented, it's a fundamental feature of reality itself. It's as if the universe has its own built-in code, and we've somehow stumbled upon the key to deciphering it. This leads us to a fascinating question. Are there limits to what we can discover through mathematics? As powerful as it is, could there be aspects of the universe that remain forever beyond our reach? That's where our journey takes us next, into the boundaries of human knowledge and the tantalizing mysteries that lie just out of sight. Have you ever wondered if there's a limit to what we can truly understand about the universe? It's a question that has puzzled thinkers for centuries. Can the human mind, bound by the laws of physics and the constraints of our perspective, ever fully grasp the origins and nature of everything around us? To explore this, let's take a step back and consider something profound. Even the most advanced tools and theories we have might not be enough to uncover every secret the cosmos holds. Take, for example, Gödel's incompleteness theorems. These groundbreaking ideas from mathematics suggest that within any logical system, there are truths that simply cannot be proven. It's a humbling reminder that no matter how much we learn, there may always be mysteries that remain just beyond our reach. Think of it like this. Imagine a fish trying to understand the concept of water. To the fish, water is everything. It's the medium it swims in, the source of its life. But could the fish ever truly comprehend what water is? From our perspective, it's obvious, but to the fish, it might be an unsolvable puzzle. In the same way, our understanding of the universe could be limited by the very framework of our existence. But here's the fascinating part. It's not just about what we can't know. It's also about what drives us to keep searching. Curiosity and imagination have always been the engines of human progress. They push us to ask questions, to explore, and to dream beyond the boundaries of what seems possible. Even if we can't fully comprehend the universe, the act of trying to understand it reveals something extraordinary about us, our relentless desire to make sense of the unknown. So, what does this mean for the future of cosmology? If there are limits to our knowledge, does that mean we should stop trying? Not at all. In fact, it's the very challenge of these unanswered questions that propels us forward. Every discovery, every new theory brings us closer to the edge of understanding, even if we never reach the end. And that's where the beauty lies, not in having all the answers, but in the journey of seeking them. As we stand on the brink of a new era in cosmology, the tools and theories at our disposal are more powerful than ever before. Picture this: the James Webb Space Telescope, floating millions of miles from Earth, capturing light from the earliest galaxies, peeling back the layers of time to reveal the universe's infancy. This isn't just a telescope, it's a time machine, offering us glimpses of stars and galaxies as they were over 13 billion years ago, and it's not alone. Gravitational wave detectors like LIGO and Virgo are listening to the faint ripples in spacetime, the echoes of colliding black holes and neutron stars, opening a completely new window into the cosmos. But it's not just the technology that's advancing. Our theories are evolving too. Take quantum gravity, for instance, an idea that seeks to bridge the gap between the tiny world of quantum mechanics and the vastness of general relativity. It's a puzzle that's eluded scientists for decades, but recent breakthroughs are bringing us closer than ever to understanding how these two seemingly incompatible frameworks might fit together. Then there's holography, a mind-bending concept suggesting that our entire universe could be encoded on a two-dimensional surface, like a cosmic projection. These aren't just abstract ideas, they're potential keys to unlocking the deepest secrets of existence. The excitement here is palpable. It's like watching a massive cosmic jigsaw puzzle slowly come together piece by piece. Each discovery, whether it's a new observation from a telescope or a breakthrough in theoretical physics, adds another fragment to the picture. And with every piece that clicks into place, we inch closer to understanding the grand design of the universe. But as we push the boundaries of knowledge, we also face profound questions, not just about the cosmos, but about our place within it. What does it mean to uncover the origins of everything? And how should we, as a species, navigate the ethical implications of such discoveries? These are the questions we'll explore next, as we continue to push the boundaries of space exploration. A question emerges that transcends science and technology. Should we explore the universe? This isn't just about whether we can, it's about whether we should. The pursuit of the cosmos raises profound ethical questions that challenge how we view our place in the grand scheme of things. For instance, consider the resources required to send missions to distant stars or build telescopes capable of peering into the early universe. Could those resources be better spent addressing urgent problems here on Earth, like poverty or climate change? Or does the quest to understand the universe serve a higher purpose, one that inspires and unites humanity in ways that ripple far beyond our planet? Then there's the possibility of encountering other civilizations. What if we find life or even intelligent beings out there? How do we approach them? Do we have the right to interfere with their existence, or should we adopt a principle of non-interference, much like the prime directive from science fiction? These aren't just hypotheticals, they're moral dilemmas that force us to confront our values and responsibilities as a species. And what if we discover resources on other worlds? Do we exploit them, or do we act as cosmic stewards, preserving the beauty and diversity of the universe for future generations? The idea of cosmic stewardship is particularly compelling. Imagine humanity not as conquerors of the cosmos, but as caretakers, guardians of its wonders. This perspective shifts the narrative from exploitation to preservation, encouraging us to think beyond our immediate needs and consider the long-term impact of our actions. It's a humbling thought, but also an empowering one. By embracing this role, we could redefine what it means to be a spacefaring civilization, prioritizing harmony over dominance. These ethical questions aren't just intellectual exercises. They shape the way we approach space exploration and our understanding of the universe. And as we grapple with these dilemmas, we're also reminded of the cultural significance of cosmology, how the stories we tell about the cosmos reflect our deepest hopes, fears, and aspirations. This brings us to the next chapter of our journey, exploring how humanity's quest to understand the universe has shaped art, philosophy, and culture throughout history. Throughout history, humanity's quest to understand the universe has not only shaped science, but also deeply influenced our art, literature, and philosophy. Think about Van Gogh's iconic painting Starry Night. Those swirling, luminous skies aren't just a masterpiece of color and movement. They're a reflection of our fascination with the cosmos. Van Gogh once wrote about the night sky as a source of profound inspiration, a reminder of the infinite and the mysterious. His work captures that sense of awe, the same feeling we get when we look up at the stars and wonder about our place in the vast expanse. This connection between the cosmos and creativity isn't limited to art. Literature, too, has been shaped by humanity's cosmic curiosity. From ancient myths about the stars to modern science fiction, stories have always explored the mysteries of the universe. Carl Sagan, the renowned astronomer and science communicator, once described the cosmos as a way of thinking, a way of knowing, a way of being. His book Cosmos and the accompanying television series didn't just explain the science of the universe. They invited us to see it as a source of wonder and unity, a shared heritage for all of humanity. Philosophy, too, has been profoundly influenced by our understanding of the cosmos. The ancient Greeks looked to the heavens to ponder questions about existence, purpose, and the nature of reality. Today, modern thinkers continue to draw on cosmology to explore these timeless questions. The idea that we are made of stardust, for example, a concept rooted in science, has become a poetic reminder of our connection to the universe. It's a thought that transcends culture and time, resonating with people across the globe. What's truly remarkable is how these cosmic themes bring people together. Whether it's through a painting, a book, or a philosophical idea, the universe has a way of sparking conversations that bridge generations and cultures. It's a universal language, one that speaks to our shared curiosity and our desire to find meaning in the vastness of space. And this isn't just about looking outward, it's about looking inward too. The awe we feel when we contemplate the cosmos often leads to a deeper understanding of ourselves and our place in the world. It's a reminder that, even in the face of the unknown, we are all part of something much larger than ourselves. That sense of connection, that spark of wonder, is what makes cosmology so deeply personal and so universally inspiring. This interplay between the cosmos and culture doesn't just shape how we see the universe, it shapes how we see ourselves. And as we continue to explore the mysteries of space, we're also uncovering new ways to connect with one another, to dream, and to imagine what might lie beyond the stars. Have you ever stood outside on a clear night, looked up at the stars, and felt a sense of wonder so profound it stopped you in your tracks? That moment when the vastness of the universe seems to stretch endlessly above you is more than just awe-inspiring, it's transformative. Understanding how the universe began isn't just about unraveling the mysteries of science. It's about connecting with something much larger than ourselves. It's about finding perspective, purpose, and even a little bit of peace in the grand scheme of things. Think about it, every atom in your body, every breath you take, every star you see in the night sky, they all trace back to the same cosmic origins. The same forces that shaped galaxies billions of years ago are still at work, shaping the world around us and even within us. When we study cosmology, we're not just exploring the past, we're discovering how deeply intertwined we are with the universe itself. It's a reminder that we're part of something extraordinary, something timeless, and that's where the real magic lies. Cosmology doesn't just answer questions about how the universe began, it encourages us to ask new ones. It sparks curiosity, pushing us to look beyond our everyday lives and ponder the bigger picture. It teaches us humility, too. In a universe so vast, with billions of galaxies and trillions of stars, our problems, no matter how big they seem, start to feel a little smaller. Not less important, but part of a much larger tapestry. It's a perspective that can bring clarity, even comfort, in moments when life feels overwhelming. Take stargazing, for example. When you look up at the night sky, you're not just seeing distant points of light. You're seeing the echoes of the Big Bang, the remnants of ancient stars, and the birthplaces of new ones. It's a connection to the past, present, and future all at once. And in that connection, we find meaning. We realize that our existence, fleeting as it may be, is part of an ongoing story that began billions of years ago and will continue long after we're gone. That's a humbling thought, but also an empowering one. It reminds us that we're not just observers of the universe, we're participants in its unfolding. As we've journeyed through the mysteries of the universe's origins, from the Big Bang to the formation of galaxies, we've uncovered not just the science behind it all, but the profound impact it has on how we see ourselves and our place in the cosmos. Cosmology isn't just about understanding the universe. It's about understanding what it means to be human in a universe so vast, so complex, and so beautifully mysterious. And that's a journey worth taking. So, what have we discovered on this journey through the origins of the universe? From the explosive birth of the cosmos in the Big Bang to the mind-bending possibilities of the multiverse, we've explored how the universe might have begun and where it could be heading. We've wrestled with profound questions. What is time? Will the universe expand forever, or will it collapse back into itself? And where does humanity fit into this grand cosmic tapestry? These aren't just scientific inquiries, they're deeply human ones, connecting us to the very fabric of existence. The Big Bang Theory gives us a starting point, a moment when everything we know, space, time, matter, burst into being. But it's not the end of the story. Inflation theory suggests that the universe expanded faster than light in its earliest moments, while quantum fluctuations hint at the seeds of galaxies and stars. And then there's the multiverse, a concept that stretches our imagination, proposing that our universe might be just one of countless others, each with its own laws of physics. But cosmology isn't just about understanding the universe, it's about understanding ourselves. As Carl Sagan once said, we are a way for the cosmos to know itself. Think about that for a moment. Every star, every atom, every galaxy is part of a story that we, as conscious beings, are here to witness and explore. It's a humbling thought, and yet it's also empowering. We're not just passive observers, we're active participants in this cosmic journey. So, what's next? The universe is full of mysteries waiting to be unraveled. Dark energy, dark matter, the nature of black holes, these are just a few of the puzzles that scientists are working to solve. And you don't have to be an astrophysicist to join the adventure. Every time you look up at the night sky, you're part of this quest for understanding. If you've enjoyed this exploration of the universe's beginnings, don't stop here. Share your thoughts in the comments what fascinates you most about the cosmos. And if you're eager for more cosmic discoveries, hit that subscribe button and join us as we continue to uncover the wonders of the universe. Together, let's keep asking the big questions and marveling at the infinite possibilities that surround us. After all, the universe isn't just out there, it's within us, waiting to be discovered.